So the other day, we went over one new concept. That new concept was Hooke's law, okay, which describes the restoring force in a spring, okay, being equal to negative K times X. In other words, the stiffness of the spring and how far it is stretched or compressed from equilibrium, okay, will affect the force that the spring exerts trying to get back to its unstrained or equilibrium position. Okay, so we did a few problems related to that. And we talked about elastic potential energy being 1/2 kx squared. And the reason for that was because we get it off of a force distance graph. Okay, and it's essentially calculating the area underneath this line. This force is K times X. Displacement is X. And it's a triangle, so we go 1/2 K times X, and that's where we get that formula from. Right? It's the area underneath the force distance graph. Is that ringing a bell from the other day? Okay. Then we went into this, a concept we've already gone over lots of times, the law of conservation of mechanical energy, except that this time we were looking at it in terms of masses on springs instead of roller coasters or sledders or whatever. Okay, and we said that this still is true. The initial potential plus the initial kinetic still equals the final potential plus the final kinetic. This is just the law of conservation of mechanical energy. Okay, we calculate mechanical energy by adding potential and kinetic together. All we're changing now is that this potential energy is now elastic. Kinetic is never going to change. Kinetic is always dependent on mass and speed. It doesn't matter what kind of situation we're dealing with. Something has kinetic energy if it has mass and speed. Okay? So that would be initial, and then we would have 1/2 kx f squared and plus 1/2 mvf squared, right? And in doing these, we also ran into some different terminology. Okay, they talked about the maximum amplitude, okay, and how that's kind of a special x because it's the not just the displacement, it's the biggest x can be, right? And at that position, at that maximum amplitude where x is its biggest value, all of the energy is potential, right? And then we talked about when we were dealing with the maximum speed occurs at equilibrium. Okay, so those were special positions that we needed to be aware of, okay, when we were solving those kinds of problems. Is that ringing a bell? Everybody's okay with those ideas? All right, so what I want you to do is I want you to try this question here. It's a Hooke's law question, okay? Just see how you do on that one. It's like the easiest Hooke's law question ever, okay? And then we'll look at a couple of other ones here that are more kind of conservation of energy type questions. In this question, we're told that we have a 0.60 kilogram mass and it's vibrating or oscillating on the end of a spring, so it's moving back and forth. Okay, the spring constant's 26 newtons per meter and the maximum displacement of the mass is 0.15 meters. We want to find the speed of the object at its equilibrium position. Okay, give you a little bit of time on that one. Okay, so for this one here, okay, here's the things we know. We know the mass is 0.6 kilograms. Okay, we know the spring constant is 26 newtons per meter. We know the maximum displacement or amplitude, which we could also say is xi if we wanted. Okay, but I always write amplitude if they actually tell me that. It's 0.15 meters. Okay, we're looking for the maximum speed. Okay, and that's usually the way I write it, just so I remember this one's happening at equilibrium. This one's happening at the maximum amplitude. All right, so EI equals EF, okay, which would normally mean EPI plus EKI equals EPF plus EKF, except that in this question, they specifically said the first point is at the maximum amplitude where there isn't any potential, and the second point is how fast is it going at equilibrium where there isn't any potential energy. Right, so I can cross those off right away because at equilibrium, x is 0, right? And at the maximum amplitude, v is 0. So I've got these two things here. So I'm going to say that 1/2 kx squared, okay, actually ka squared, equals 1/2 mv max squared. right? I'm trying to get that maximum speed, so I'm going to divide both sides by 1/2 of m. The halves will cancel. I need to take the square root to get v. Right? So our maximum speed will be the square root of 26 times 0.15 squared divided by 0.6 kilograms. When we do that, we should get 0.99 meters per second, but we'll just double check it here. Okay, so 26 times 0.15 squared, okay, divided by 0.6, right? 0.99 meters per second. Okay, everybody all right with how that one worked? Right. Not really much different than what we did before, okay, with MGH. It's just we're substituting in something different. This would have been the top of the hill and the bottom of the hill. Okay, so this one's a little bit tougher in that it's got a few more details in it, so just read it carefully. 0.4 kilogram mass, okay, frictionless surface, maximum speed is 0.5 meters per second, and the maximum displacement is 0.11. You're looking for the spring constant here, okay? These are going to get more difficult as we go, okay, but let's just try this one for now. Okay, so this is another one where we're comparing maximum amplitude to the, at which position? At equilibrium, because it's the maximum speed, right? Okay, so it reaches a maximum speed of 0.5. So we know when we're doing this EI equals EF, we know our initial energy is 1/2 mv max squared, and we're talking about the maximum displacement, so that'll be 1/2 Ka squared, right? And we're looking for the spring constant, so we're trying to solve for K. So we're just going to divide both sides by 1/2 of A squared. The halves will cancel, okay? And then we've got K. So we'll have 0.4 times 0.5 squared divided by 0.11 squared. Key here is to remember to square those two values, because if you don't, obviously it comes out a lot different. So we'll get 8.3 newtons per meter on that one. All right. Questions on number 8? Okay, so the way that these become a little more involved is that I don't just make them about equilibrium and the maximum displacement. I ask you to compare places that have both a displacement and a speed, right? So like halfway down a hill on a roller coaster. So you would have both potential and kinetic, and you'd have to move one of them around when you do the manipulation, right? So that would be like, not that one. Didn't we just do that? Okay. No, we didn't. But it's still maximum and maximum. Nope. Not that one either. Come on. Okay, this one's a little more involved. It's actually a two-step problem. Okay, so give that one a try. We got horizontal spring, frictionless surface. Okay, we know the maximum speed and the maximum displacement, but we're looking for the speed of the object when its displacement is 0.1 meters. So you're going to have to do one calculation to find something you need to do the second part. Okay, give you a little bit of time on that one. That one will make you think. So what we have here for givens are the spring constant, okay, 18 newtons per meter. Okay, we're told its maximum speed, so that happens at equilibrium, 0.35 meters per second. We're also told the amplitude, or maximum displacement, 0.29 meters, and we're looking for the speed of the object when its displacement, so this would be like the F, we'll say, okay, we're looking for that when its displacement is 0.10 meters. All right, what do I not know about this object right now? I don't know its mass. Okay, is that something I'm going to need if I want to calculate how fast it's going? Yeah, I can't calculate anything about kinetic energy without mass. Okay, I need mass, it's part of that formula. But here's what I can do. I can compare the equilibrium position and the maximum amplitude. I know the maximum amplitude, I know the maximum speed, and I know the spring constant. The only thing I don't know is mass. I can find it if I set those two things equal to each other. Okay, I can solve for mass because I have the other three things in that formula. So that's the first thing I want to do. So mass will equal Ka squared divided by V max squared, right? The halves cancel off. All right, so I'll have the 18 times 0.29 squared divided by 0.35 squared. All right, so that'll get us our mass. So 18 times 0.29 squared divided by 0.35 squared, 5 squared, gives us, all right, so the mass is 12 kilograms, 12.35 kilograms. All right, so now I've got that. Now I can do another law of conservation of energy question, but now I'm going to use this as my second point. I can use either this or this as the initial point because I have all the information for both. Okay, so what I'm going to do is I'm going to use the stuff I was given. Okay, I'm going to use 1/2 Ka squared equals 1/2 Kxf squared plus 1/2 MVF squared. Right, this is what I'm looking for. Okay, so I need to isolate that. So I'm going to bring the 1/2 Kxf over here. So I'll have 1/2 Ka squared minus 1/2 Kxf squared equals 1/2 MVF squared. Then I'm going to divide both sides by half of M. Okay, and square root that. Right, so that'll give me that. I could have canceled the halves at any point as well because it was in every term. I could have gotten rid of them. Okay. So what we'll be looking at here is Ka squared minus Kxf squared. Sorry, I should put in the numbers here. 18 times 0.29, right? It was 0.29. Yeah. Squared minus 18 times 0.11, right? It was 0.10 squared, okay, divided by the mass we calculated, 12 points, whatever. Okay, so when we do that, okay, that should give us our our speed of 0.33 meters per second. Okay, and that's a logical answer because obviously the maximum speed was 0.35. This speed would have to be slower than that because it's not quite as far out as the other one was. Okay. All right, everybody okay with that? That's about as tricky as they would get. Okay, in terms of a law of conservation of energy question, that one requires you to do 2 steps in order to get to the full solution. Not that one. Okay, I want you to try this one. This is Hooke's law a little bit. Okay, so we have a 75-gram object. Okay, vibrating with simple harmonic motion at the end of a spring whose spring constant is 5 newtons per meter. The maximum displacement of the object is 0.080 meters. What's the maximum acceleration? Okay, all right, so we're looking. It's a 2-step problem. Okay, you're going to have to do one thing to get something you need for the second part. Okay, but it's quite a bit different first and second than the last. Okay, so let's have a look at this one, right? We know the displacement of this thing. We know its amplitude, maximum displacement is 0.08 meters. We know its mass is 0.075 kilograms. Okay, and we know the spring constant is 5.0 newtons per meter. Since it's a horizontal spring, actually they don't even say that, but okay, it's saying it's vibrating with simple harmonic motion. Okay, we know that the force in the spring is the only force that is acting. Okay, because it doesn't mention gravity, doesn't mention being a vertical spring or anything like that. Okay, so we know then that negative K times X is our force. Right? If we're going to find the maximum acceleration, that occurs at the maximum amplitude because that's where the force is the greatest. Okay, the more I compress the spring, the harder the spring pushes. So when I get to that maximum spot, that's where the spring pushes the hardest. That's where my acceleration will be at its maximum. So I just need to divide both sides by mass, which is why I have to make that conversion to kilograms. And I'm just going to have negative 5.0 times 0.08, which I'm going to leave as a positive number, okay, divided by our 0.075. Okay, and that'll give us our 5.3 meters per second squared, which should actually be negative. All right. Now, it's negative for me because I decided that that 0.08 would be positive, but they never actually said whether the spring was compressed or stretched. Okay, and that would make a difference. If it went to the right, then the acceleration would be to the left. Okay, if it went to the left, then the acceleration would be to the right. They never really say that in the question, so okay, I'm just saying it's negative the way I set it up. All right, so kind of a basic Hooke's law kind of a question there. And that's all I've got for that one. Something else I wanted you working on here. Hang on.